Ladies and gentlemen, let's continue with chapter 6 that we are busy with in the textbook of Cengel and Ghajar. Chapter 6 is on the fundamentals of convection. With the previous lecture, we discussed the fundamentals of convection, and we looked at the boundary layer theory. We did a quick revision of the different types of flow that you can get, unsteady and steady, etc. And then we've revised what you've done previously in fluid mechanics, and that was then specifically the boundary layer theory. And at the end of the lecture, we have ended with looking at what happens in a tube with a friction factor as a function of Reynolds. That is a linear relationship on a log-log scale, and that value is actually 64 divided by the Reynolds number. And if it is a smooth tube, then for this would be for 0, and then for all the other tubes, the rougher tubes, the data would be there. That is important for us to determine the friction factor, because the friction factor determines pressure drop, and pressure drop costs money. Why do we look at something like the friction factor in a course like heat transfer, as well as the shear stress over a flat plate, how it varies as a function of Reynolds number? Because I'm going to show to you later on that in heat transfer, many of the practical problems we are going to ask you is you will have to determine the heat transfer rate, the heat capacity of the heat exchanger, but also the pressure drop, because those are the two things that we are normally interested in, and they are in all cases actually connected to each other. Okay, so what we see is that the friction factor or the shear stress is a function of Reynolds number. That is for a specific Reynolds number, and if we would specifically look at a Reynolds number at a flat plate, we will actually see that the boundary layer develops, and tau, the shear stress, is not constant. It varies along the position in the plate. But from fluid mechanics, you know that this shear stress at any point there is equal to the viscosity multiplied by the velocity gradient at the wall. Now, this might be theoretically, and it is theoretically, but for us as engineers, it's a very difficult thing to work with, because as you can see, the shear stress is not a constant. Therefore, we are normally more interested in the average. And for the average values, we would say that the average shear stress is equal to the friction coefficient, CF, or the skin, or it can be called the friction coefficient or the skin friction coefficient, CF, multiplied by rho v squared divided by 2. So that is a little bit of a revision of your fluid mechanics. Now let's introduce paragraph 6.4, the thermal boundary layer. Now the thermal boundary layer is very much the same as the velocity boundary layer. So if this is maybe a flat plate, and we look at the flow over this flat plate, there is the velocity, and now we want to go and measure the temperature. Well, the first problem we have is that temperature is not a vector. Okay. But nothing keeps us, if that temperature is 100 degrees Celsius, to use a line there of 100 millimeters. So that also gives us an indication of the temperature, how it varies as a function of not x, but as y. Now there is the plate, and what we will see is that on the plate, this plate will have a certain surface temperature. Now let's suppose the surface temperature is 20 degrees Celsius. From measurements, what we see is that that temperature, which is 20 millimeters, 20 degrees Celsius. If we now make it a length of 20, then we get something very similar to that of a boundary layer. As you can see, my scale is not right here. That should be 100, and that should also be 100. Okay, 100, and then it starts reducing there to a smaller value. So as you can see, it's almost the same, but it is not the same. So how are we going to handle that? Well, we do it by saying that the thermal boundary layer thickness, the boundary layer thickness for a velocity gradient was just delta. This one is now delta T to indicate it is a thermal boundary layer. That would be equal to 0.99 times the free stream temperature minus the surface temperature. Okay. Now let's look at the example of the free stream temperature, which was 100 degrees Celsius, and the surface temperature, which is 20 degrees Celsius. Then it means delta T is where we've got 0.99 multiplied by 100 minus 20, and that is equal to 79.2 degrees Celsius. Thus, if we now go down here, we keep on measuring 100, 100, 100, then it's going to decrease, and then to the point where it is 79.2. That would be the thermal boundary layer thickness, delta T. Okay. And this gradient here will give us the heat transfer coefficient. So the heat transfer coefficient is equal to minus the K of the fluid multiplied by the T dy, where y is equal to 0, divided by Ts minus T infinite, and we have derived that previously. So in fluid mechanics, this velocity distribution gives us the shear stress. In heat transfer, this temperature gradient gives us the heat transfer rate, or the heat transfer coefficient. You follow that? Okay, so it's very much the same. Now let's introduce a next non-dimensionalized number, which is known as the Prandtl number. Now, the Prandtl number, by definition, is the molecular diffusion of momentum divided by the molecular diffusion of heat. Now, what does diffusion really mean? Diffusion means the movement of particles. The movement of particles. So the Prandtl number is the ratio of the movement of particles because of momentum divided by the movement of particles because of heat. And that gives us an indication of the relative thickness of the velocity boundary, the velocity and thermal boundary layers. And it is equal to the viscosity multiplied by Cp divided by thermal conductivity. So it's all properties, fluid properties, and if you want to, you can also write it as the kinematic viscosity divided by alpha. Now, Prandtl was a very interesting guy. He lived from 1875 to 1953. He was a German engineer. And Prandtl is considered as the father of aerodynamics. So all of you interested in aerodynamics that you're going to take in the second semester, he was the guy who actually developed the whole theory of a velocity boundary layer. And analytically, he was very, very strong mathematically. And he developed many of the theories that was used 50, 60 years ago by design engineers to predict the lift of aerofoils, specifically thin aerofoils. And he developed the so-called lifting line theory. Now I see what is very interesting from him is, except now where he studied, etc., is that he's considered, his life was marked by overtones and naivety. At the age of 34, he decided it was time to marry, so he went to his supervisor, his professor, which was Professor August Foppel, to ask his daughter's hand in marriage. But his supervisor actually had a few daughters. And when his supervisor arrived at home and told his wife, they didn't know which daughter it was actually that he wanted to get married. So they discussed it hurriedly. They discussed it quickly amongst themselves and decided it should be the older one. And that was fine. The marriage was long and a happy one. So that was one of the strange things of Prandtl. But it is somebody that has made a huge impact on fluid mechanics and aerodynamics just a little bit than 100 years ago. Okay, now, where's my page? Here it is. Okay. So, in terms of understanding what this now actually means, I'm going to show it to you schematically in terms of the velocity boundary layer. BL is just boundary layer, and this would be the thermal boundary layer. On a flat plate, and we are going to consider three cases. The first case where the Prandtl number is smaller than 1. The second case where the Prandtl number is approximately 1. And the third case when the Prandtl number is larger than 1. Now I'm going to do it a lot. The velocity boundary layer I'm going to indicate in blue. So let's show a typical velocity boundary layer. And as I've explained previously, that is the boundary layer thickness, delta. So all of them would be delta. And I'm going to put the same velocity boundary layers there in blue to indicate them. But now I'm also going to put in the thermal boundary layer. What the thermal boundary layer would do relative to the velocity boundary layer. Prandtl number smaller than 1, we will get something like that. So that would now be the thermal boundary layer. If the Prandtl number is equal to 1, then the two boundary layers will fall on top of each other. And if the Prandtl number is larger than 1, then the thermal boundary layer would be smaller than that of the velocity boundary layer. So if it is smaller than 1, it means that heat diffuses quickly. Okay. And if the Prandtl number is larger than 1, it means that the heat diffuses slowly. So So Prandtl numbers smaller than 1 means the heat diffuses quickly, and when they're larger than 1, then they diffuse slowly. This one, Prandtl number equal to 1, has very special mathematical advantages. And that you will see later on in the theory when the energy equation is used together with the momentum equation, then all the terms can be written as a function of Reynolds number and Prandtl number, etc. And the moment when the Prandtl number is equal to 1, then it is so much easier to solve the equations. Yep, question?
The shape of the boundary layer is always the same.
Sorry?
Is the shape of the boundary layer is always the same?
No, it's going to be a function of Reynolds number. So at any specific point, this thickness of the boundary layer is going to be a function of the Reynolds number only. Okay, and it's a Reynolds number to the power of x, and that is what's going to determine the relative thickness of the boundary layer. In the case of the thermal one, the Prandtl number is going to influence the thickness of the thermal boundary layer. Now, just to give you an indication of typical fluids and the Prandtl numbers. So liquid metal will have Prandtl numbers approximately in the order of 0.03. Typical liquid metals which are being used in heat transfer is something like mercury, and it has been tried, or similar liquids are being tried in the nuclear industry, especially where they want to get heat transfer away very quickly from the nuclear rods. Gases have Prandtl number of approximately 1 order of magnitude. The Prandtl number of air at 20 degrees Celsius is about 0.7, but many of the gases order of magnitude about 1. Water, Prandtl number of order of magnitude 10, while oils will have Prandtl numbers of order of magnitude of 50 to 100,000, and glycerine will have Prandtl numbers of approximately 2,000 to 100,000. Right, now I'm going to skip 3 parts in the textbook. The first one is on laminar and turbulent flow, which you've already done in fluid mechanics. With the previous lecture, I've also revised it very quickly. And then there's a paragraph on heat and mass transfer in turbulent flow. Again, where it just shows the effect of the turbulent, the velocity, which is equal to a constant plus a fluctuation, and the same with temperature. And then there's the derivation of the differential equations, and at the moment you are doing it in MKM, and you've also done it last year in MTV, so therefore we're going to skip that. So we are going to go now to paragraph 6.8, which is the solutions of the convection equations. The solutions of the convection equations. And the solution is for the easiest geometry and the most simple case of fluid mechanics that we know. So it is at a specific temperature T infinite with a velocity V, and that would be the coordinate system there would be Y, and that would be X, and that would be the boundary layer that forms in laminar flow. Now, if we do that and we look at the momentum equation or the continuity equation first, then we can see that du dx plus dv dy is equal to 0. Then the momentum equation, which is u multiplied by partial du dx plus v partial du dy is equal to the kinematic viscosity multiplied by partial d2u dy squared. Dy squared. And then the last one, the energy equation. The energy equation is equal to u, the partial dt dx, plus v, partial dt dy, is equal to alpha multiplied by partial d2 t dy squared. Okay. So, take note, this is in terms of your fluid mechanics and what you're doing in MKM now, a case where we've made almost all the assumptions. The density is zero, it is a Newtonian flow, etc., 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 and the flow is the simplest case of two-dimensional. So if we just go back to the Navier-Stokes equation, if one of you can get the analytical solution for the Navier-Stokes equation, then you will most probably get the Fields Medal. The Fields Medal is the same as the Nobel Prize medal for physics and chemistry. There's no Nobel Prize for physics, but there's the Fields Medal, which is the Nobel Prize for mathematics. So if one of you can figure out the analytical solution for the Navier-Stokes equation, I'm quite sure you might probably get the Fields Medal. Now in the meantime, people before us have tried to make this as simple as possible, because normally, if you can solve the simpler cases, it is easier to go to the more complicated cases. Now this was done by a student with the name of Blasius in 1908, which was a student again of Prandtl. Now what Blasius did is, after he've looked at this equation many times, and he've tried many different types of approaches, he decided, I'm going to define a value of eta, which is equal to y multiplied by v divided by the kinematic viscosity x. I'm going to define the similarity variable, and together with that I am going to make use of the principle of stream functions. U is equal to deep c dy, and v is equal to minus deep c dx. So these are stream lines, and those are the velocities. And then he figured out that these three equations with three boundary conditions, of course the boundary conditions would be the velocity on the walls is equal to 0, and a similar thing for the thermal boundary layer. He would use all that, and then he came up with a differential equation, a third order differential equation, which was 2 times d3f d eta 3 plus f multiplied by d2f d eta square is equal to 0. So he then derived this third order differential equation, and he defined a function f, which is a function of eta, which is equal to the stream function divided by the velocity Vx divided by phi, by the velocity. Now he didn't get that right just by sleeping in his bed or having dinner somewhere and came up with this bright idea. He came up after many hundreds of hours trying to solve this equation. So it was a long road for him. So it's not so obvious if you look at that. So it came by iteration. Now this equation can actually be solved by power series expansion. And the moment you've got a power series, it means it's the sum of many different things. And then later on, about 50, 60 years ago, with the first computers, they realized they can also solve it with the Runge-Kutta method, typically the fourth order one. I'm quite sure all of you are familiar with that. And then he came up with a solution of eta f df d eta and d2f d eta squared. And typically for 0, this value was also 0, and that one was 0, and that one was 0.332. And then for a value of 0.5, it is equal to 0.042 and 0.166 and 0.331. Now, if you look at this, you will ask me, but what does this now have to do with that? What is the relationship? I'm going to show it to you just now. So then you can do it for a 0.1 and 0.166, and again for so many values. And then there's a value of 4.9, where this is equal to 0.99. There's another value there. And if it is 6, then typically this value is 4.2, and that one was 0.999 and 0.002. Okay. Now, Blasius figured out two things, which is not so obvious if you look at this very quickly. The first one is that the f d eta is actually equal to u divided by v, where in a boundary layer that would be v, so it's the free stream velocity. It's the velocity divided by the free stream velocity. Now, we have said the definition of the boundary layer thickness is where this is equal to 0.99 times V. You remember? So that's the boundary layer thickness. So he realized that this 4.91, eta value of 4.91 is where the velocity distribution gives the boundary layer thickness. That is what he figured out. So that was the first thing that he figured out. And then there's something else there, a value of 0.332, which is also special, and I'm going to get to that just now. So what Blasius figured out is going to this thing of eta, which is equal to y multiplied by v, kinematic viscosity divided by x, the similarity variable that he figured out. He figured out, well, at this very special condition, eta is 4.91. Okay, do you see? And that is then equal to y is the boundary layer thickness that he actually now wants to solve. That's the value of y. That value there. Square root of the velocity divided by the kinematic viscosity x. If you do a little bit of manipulation, then you can now actually solve the boundary layer thickness equal to 4.91, the square root of the velocity divided by the kinematic viscosity x, which you can also write as 4.91 times multiplied by x divided by the square root of the local Reynolds number. And that was a brilliant derivation. And for the first time, they could actually then determine analytically what the boundary layer thickness is going to be. Why is it important? Well, 50, 60 years ago, all aircraft were designed using this very simple empirical equation. It opened up many, many doors for them. Now, this one is also special because in a similar way than solving the boundary layer thickness, this value is then can be used as, or this will then be equal to 0.664 Reynolds, local Reynolds number x to the minus a half. Now you would look at this and say, but okay, this is 0.664, it is not 0.332. Well, it comes from the fact that the drag force is equal to CF multiplied by the area, rho v squared divided by 2. So this value of 2 divided by this value of CF, obviously you need to do a little bit of manipulation, then that is 0.332 multiplied by 2. That is where it comes from. You're not going to see it directly on the board, but just go and do all the mathematics at home, and then you'll see that that is indeed the case. Where, just for in case you cannot remember, the Reynolds number, the local Reynolds number is equal to the velocity, the value of x divided by the kinematic viscosity v, that v like that, where that viscosity is equal to our normal viscosity divided by the density. So sometimes we can go through all this very quickly and we can just go and select the results without really having a good appreciation of the excellent work that other people did before us. Okay, now if we go and do a little bit of manipulation, then we can derive that the Nusselt number, the local Nusselt number, at any point is equal to the heat transfer coefficient at a point x multiplied by x divided by k, and that is equal to 0.332 multiplied by Prandtl to the third Reynolds x to the half, and that would be for Prandtl numbers larger than 0.6. And in general, it can then be showed that the boundary layer thickness, the velocity boundary layer thickness divided by the thermal boundary layer thickness is approximately equal to Prandtl to the third. Or then the thermal boundary layer can be written as 4.91 divided by the Prandtl to the third, the local Reynolds number at point x. And this is valid for laminar flow. For laminar flow and Prandtl approximately equal to 1. Let's look at a simple example just to give you a little bit of a feeling for the boundary layer thickness and the thermal boundary layer thickness. So let's consider a plate for which we've got a free stream velocity of 1 meters per second. Okay. A Mach getal smaller than 0.3, which means that it is incompressible. The Prandtl number is equal to 0.7309. The viscosity, the density is equal to 1 kilograms per cubic meter. And the viscosity is equal to 1 multiplied by 10 to the minus 5 kilograms meters per second. And we would like to get the solution at 0.5 meters from the leading edge, 500 millimeters, as well as at 1 meters from the leading edge. Okay. Now, let's go and look at x equal 1. At x equal 1, the Reynolds number at that point is equal to rho Vx divided by the viscosity. The density is 1, the velocity is also equal to 1 meters per second, and we would like it at a distance of 1, and the viscosity is 1 multiplied by 10 to the minus 5, and that would then be equal to 1 multiplied by 10 to the 5th. Now the boundary layer thickness at x equal to 1 would then be equal to 4.91 multiplied by multiplied by x is 1 meters, divided by 1 multiplied by 10 to the 5th, and it should be the square root of it, and that would then be equal to 15.5 millimeters. 15.5. Okay. If you go and do a similar calculation at x equal to 0.5, then the boundary layer thickness at 0.5 will be 10.99 millimeters. Okay? Now, in terms of the thermal boundary layer, the thermal boundary layer at x equal to 1 would be lambda divided by lambda t is equal to Prandtl to the 3rd. So the boundary layer thickness is equal to 0.0155 divided by the thermal boundary layer is equal to the Prandtl number 0.7309 to the 3rd, from which we can solve the thermal boundary layer is equal to 17.24 millimeters. And we can do the same at x equals 0, 0.5. Then the thermal boundary layer would be equal to 12.19 millimeters. Right, let's just show it schematically. So if that is the plate, and this is the velocity boundary layer, and that is at 0.5 meters from the leading edge, and that is 1 meters from the leading edge. Then this would be equal to 10.98, and that would be equal to 15.53. The Prandtl number is 0.7, so he diffuses quickly, so the thermal boundary layer is thicker. So if we plot the thermal boundary layer, it's something like that, and that distance thickness will be 12.19 millimeters, and that would be 17.24 millimeters. So you can go and imagine one or other object, like maybe an Airbus wing, okay, and when it just starts on the runway, and it starts moving, it's already 1 meters per second, then that would be an approximately thickness of the boundary layer, 10.98 millimeters at 500 millimeters from the leading edge, and it will be approximately 15.53 millimeters, 1 meter from the leading edge. And again, I want to emphasize that this is the analytical work that was used to design many, many generations of aircraft. Okay, now paragraph 6.9 is the non-dimensionalized convection equations of similarity. What they do in that paragraph is they non-dimensionalized this continuity equation, the momentum equation, and the energy equation. And then they wrote it in terms of Reynolds numbers and Prandtl numbers, where the Reynolds number is equal to the velocity multiplied by L divided by kinematic viscosity. So don't get confused with the L and the X. The X just shows at a specific point. The L will typically show the total length of an object. And the Prandtl number is equal to Cp multiplied the viscosity divided by the thermal conductivity. And in this paragraph, which is quite mathematical, they're going to show a very important principle, and that is that the Nusselt number is constant if the Reynolds numbers and the Prandtl numbers, now I'm going to call it an object 1 and an object 2. So this Nusselt number 1 and this Nusselt number 2, which can be associated with a Reynolds number 2 and a Prandtl number 2. So if you've got two similar types of geometrical bodies, which have the same Reynolds number, a Reynolds 1 and a Reynolds 2, and a Prandtl 1 and a Prandtl 2. If the Reynolds numbers and the Prandtl numbers are the same, then the Nusselt number of the two bodies would also be the same. It's a very important piece of mathematics with a wonderful similarity of what is happening in nature. Now this might seem a little bit of abstract, but let's look at a practical example. Let's suppose you're involved in a submarine, the design of a submarine. And this submarine typically has a length of 170 meters. Okay. And its velocity of the submarine is 60 kilometers per hour. And this submarine is there somewhere underneath the ice, and the temperature of the water on the outside is 0 degrees Celsius. Now that's a very important heat transfer problem to solve, because if the water on the outside of the submarine is 100 degrees Celsius, the people are going to freeze to death on the inside. So you need to know how much heat transfer must I put in there, how much heat must I put in with an air conditioning and ventilation system to maintain this temperature at 20 degrees Celsius. Now doing an experiment like this, building a submarine of 170 meters and getting it to move underneath the ice at 60 kilometers per hour with that temperature and then taking the measurements. Of course you can do it, but it's very, very expensive. So what do engineers do? Well, they built a lab model, a scale model, much smaller. Let's suppose 1 meters. Okay? And if we now want to think of this similarity, what it actually means that if we can build this scale model so that this Reynolds number and that Reynolds number is the same, and the Prandtl number of the medium in which it operates are the same, then the Nusselt numbers would be the same. So this is a very inexpensive type of way how you can exactly determine what the heat transfer will be. As you know, we don't only do it in heat transfer, but we also do it in fluid mechanics with the design of aerofoils. A scale model is built, a smaller model that fits into a wind tunnel. So now let's just look at typically the practical examples. Unfortunately, it is not always so easy. So if we look at this Reynolds number, rho v d, I've used d, it is just a characteristic length. We're going to use L and the viscosity. And for this case, the Reynolds number must also be rho v d divided by the viscosity. Now, before we even get to the Reynolds number, we can say, well, if we want to keep this Prandtl number of the submarine the same as this Prandtl number, then this operates in water. So if we make this model and it operates in the water at about the same temperature, then we've got the Prandtl numbers sorted out. You agree? So the Prandtl number will be approximately 6 point something. And this Prandtl number would also be 6 point something if we now use just water. And the water is at 0 degrees Celsius. And here we can do the same. We use water at 0 degrees Celsius. So the Prandtl 1 and the Prandtl 2 are the same. We now just need to get the Reynolds numbers to be the same. So if we now look at this Reynolds number and we want to calculate the Reynolds number of 1, then the density of the water is approximately 1,000. The velocity, 60 kilometers per hour, is about 16 meters per second. And the length of the scale model of the real submarine, is 170 meters. And the viscosity of water is approximately 1 multiplied by 10 to the minus 3. So then the Reynolds number is going to be 2.7 multiplied by 10 to the 9. So we need this Reynolds number also to be 2.7 multiplied by 10 to the 9th. And that should be the density of the water that we're going to use in the lab. It's also going to be 1,000. Then we need to know what the velocity should be of our scale models, V2. And the length our scale model length is 1. And the viscosity is also 1 multiplied by 10 to the minus 3. And then we are going to end up with a little bit of a problem, but a theoretical good solution. And that is that this velocity, the velocity of our model should be 2,700 meters per second. Okay, so practical, this cannot work. Okay, so it's not a good solution at all. Of course, it's going to create some problems with compressibility. We don't want compressibility issues, but theoretical, you understand what I'm trying to do. In cases like this, what they typically do is they change the fluid to something else, because then you have much more control over the Reynolds number. The moment you change the fluid, then the Prandtl number, which is also equal to Cp, the viscosity, and K, that changes. But if you go and select the right fluid, then you can get this Reynolds number or this velocity to decrease significantly. So let's suppose it should actually be 27 meters per second. Now that's still fast, but it can be done. The moral of the story, however, of this very important paragraph is that if you can do experiments where the Reynolds number of your one object is equal to the Reynolds number of the other one, and the Prandtl numbers are the same. So if Reynolds 1 is equal to Reynolds 2 and Prandtl 1 is equal to Prandtl 2, then it would mean that the Nusselt number 1 would be equal to the Nusselt number 2. So if we can sort out these fluids and the velocities, and in many times it can be done by iteration, you can get a good solution. But if you can get it to be the same, then it means that in this experiment where you're going to have the lab model, where you're going to test it, and you're going to determine the heat transfer rate, and from it the Nusselt number, then that Nusselt number will be exactly the Nusselt number of the real model, of the real submarine. Thanks, ladies and gentlemen.